Bring it around. All right, let's do this. Let's get started here. Do the drawing. I still haven't come up with the actual prize besides taking something away from you if you're not here, but we'll go. Ethan. Welcome, Ethan. All right. Jay. Jay? No? No Jay. Oh man, it's not that exciting, right? Like, I mean, it's kind of fun, right? Like this guy, poor Jay, he might have been here every time and then his name got drawn. Like, you're winning something, but then you actually lose. Grace. Oh man, there's two this time. Grace and Jay. Grace and Jay. Well, sucks to be those guys, huh? All right, but you guys have been doing pretty good. It's been a pretty full class. Last year, it got real small because everybody was just watching the videos online. And I don't want to take the videos away, so. Nope, this is the wrong class. You don't want to know about pre-stressed concrete, right? No. This one. Okay. So we're in the middle of this, right? We've moved on. Like we mentioned before, we have, to this point, we've always just given you, like, here's the acceleration equation, right? And now we need that stuff still, right? We figured out how to solve it when we're given the acceleration equation. And then today we're going to get into, or what we started last time, we're getting into where we don't get given that acceleration equation. We have to derive the acceleration equation. We have to come up with the acceleration equation, right? And what's really, I mean, honestly, I think from here on out, things get a little bit easy because there's a really strict protocol that you can follow to lead you to these right answers. And really, you just follow it just from start to finish. It works every time. Okay, so what we did last time, we're going to do F equals ma. So in this kinetics, we're going to do F equals ma, we're going to do work energy and impulse momentum. We're going to do those three different techniques. Today we're going to talk about F equals ma, Newton's second law, right? And then we're going to do it in Cartesian coordinates, then we're going to do it in normal tangent, and then we'll do it in polar coordinates, and then we'll move on to work energy. When we get done with this F equals ma, that's the last topic that's going to be viable on the exam, which in a couple weeks, okay? So next week's homework is going to be focused on this F equals ma stuff, and then you'll get done with that, you'll get some feedback, and then that next week is when you do, we're going to have the first exam, okay? It's just going to have two problems on it, just a little foreshadowing. It's going to have one kinematics problem, and it's going to have one F equals ma problem, okay? Okay. And so what we did so far, right, we just said that it's literally just like this. We look at the vector form of some of the forces, the external forces equals mass times acceleration. That's Newton's second law. And we just break it into the I components, J components, and K components. And all the I components have to be equal to each other. All the J's have to be equal to each other. And all the K's. Kind of just three separate problems kind of is how it works out, okay? And so then these are our three equations that we use. These right here are called the equations of motion. And a lot of different, just in mechanics in general, you'll see this if you stick with this and go on into some upper level stuff. You'll see equations of motion quite a bit. Okay. And so when we do these things, right, we have to sum these forces, right? We have to sum these forces, and the best way to do that is to have a free body diagram. Okay. Like I said, I'm going to have a little checklist, right, to kind of help us do this, right? Like I said, it's going to be very structured. The checklist doesn't have to be done in this order. It's not really like, it doesn't have to be sequential. First thing you're going to do is isolate the object. You did this a lot in statics. Hopefully you did a lot of it. Hopefully you did it in statics. You needed a lot here. You're going to isolate the object is the first thing you have to do, right? In particles, it's just going to be a dot, right? Because for the most part, it's a concentrated mass, so we can just turn it into a single dot. We're going to replace supports with appropriate forces and moments. That's the next step we're going to do. The third thing we're going to do is we're going to sketch applied loads or forces. Fourth thing we're going to do is pick a coordinate system. And label on diagram. We're going to see this is really important step. You got to have your coordinate system and you have to label it so that when you start summing your forces, you know what's positive and what's negative and stuff as you go through. Right? And then we're going to label dimensions. Come on. Dimensions, angles, on diagrams. That's also an important component too, is to do that. And we're going to do some examples where we go through this, just kind of refresh your memory, but a little checklist. Make sure you do all these things. Some of the key ones that people forget sometimes is the coordinate system. I even forget it sometimes. Labeling dimensions and stuff, that's also important, okay? And then how we're going to solve these problems in general, I'll give you a procedure for this as well, right? I'm going to start, as I said, very procedural from here on out. First thing we're going to do is we're going to draw a free body diagram. Right? Make note that this is worth points. Right? If you skip this, I mean, if you get to the exam and you're like, oh my God, what do I do? And then you leave off the free body diagram, you're going to get less points. If you just, at the very least, try a free body diagram, you're going to get some points because you know that that's the first step you have to do. Okay? I would just recommend following all these steps. Okay? Do it. I know sometimes you don't want to, but just do it every time. Write down equations of motion. Okay? That's the second step. Those equations of motion that we have before, I write them out every time. Even if I don't need them, I just write them all out. Some of them will just go away. But I write them all down every time. Third thing, you're going to do kinematics. Kinematics. I'm going to say as required. Sometimes these kinematics, right, that's just the geometry of motion. Sometimes they're really involved. Sometimes it's not so involved, right? But as required, we're going to do some kinematics. Kinematics is what we've done in this class up until this point. And the last part is we're going to solve it. Okay? If you stick to this plan and you do these things, right, more than likely, you're going to end up with the right answer. If you end up with the wrong answer, still okay. If you followed this procedure, then you'll be some small little mistake that you'll make, and that's where you'll lose points, okay? So just stay on top of it. Follow these procedures I've given you. I've taught this class like 15 times or something like that. These work. They work, okay? All right, do the first example. So this is a mass suspended by a spring. That's my drawing of a spring right there. Mass extended by, supported by a spring, and then it's just at rest, okay? And it's undeformed shape, so it's just kind of hanging. We're holding it in the undeformed shape, and then we're gonna release it. So it's being held up initially, right? Just have that, right? Because if I transferred it over, it would sag down and it would be static. It wouldn't move, right? If it was sagging already. So we just have it in its undeformed shape, and we're gonna release it. It's gonna fall, and it's gonna oscillate. And we dealt with this. We did the kinematics of this problem a couple weeks ago, right? It's gonna actually have an oscillation that happens, a vibration. That's when those of you in mechanical engineering go on into vibrations, you'll study that. You know, what frequency does it oscillate with, right? But for now, though, we're gonna do this one. So all they tell us right now, they don't tell us that acceleration equation. We have to come up with it. So the spring is undeformed position when the mass is released. K is given as 80 newtons per meter. The mass is 1.8 kilograms, and we're supposed to find the velocity of the mass when it hits the floor. So it's gonna come down. It's gonna hit that floor. Okay. So what is the velocity when it reaches that? All right. First thing we do, literally, I just do this every time I solve one of these problems. Okay. I come in 1. Free body diagram. Yep, I'm doing something wrong there. F, B, D. I just write it out just like that every time. And I literally write down which part of the procedure I'm doing. So then we're in the free body diagram. I isolate my mass. Done. Okay. You can draw it as a little box if you want, but it's just a concentrated mass. There isn't much. Later on, we do rigid body stuff. That's going to be more important. A free body diagram, you're going to have bars attached to other bars, attached to other things. It's important to draw the whole object, but with particles, it's concentrated, right? So then what forces are acting on this guy over here? Gravity. Yep, gravity be one, right? That was a fun one, just yell out. Just yell out gravity. That's usually always there, right? Mass edge gravity acted down. What else?
Well, you technically have the spring force, but at this instant, there's
no
force because it's not spring.
Yep. So if I displaced it a little bit, it would be there, right? It's going to be there pretty quick. Good point, right? So that's going to be up like that, right? And then it is going to be its force is going to be K times X, right? Right, like you said, when X is 0, there's no force. But as soon as X becomes something, it's gonna have a value. That's it, right? Those are the only two forces that are acting. There's no supports or anything like that, right? We have mass edge gravity going down, Kx going up, right? Next part of my free body diagram checklist, right? Isolated my object, supports, sketch applied loads and forces, done all those. Pick coordinate system and label on the diagram. Okay, we haven't done that yet. And then label dimensions and angles and stuff that are important, right? So I get to pick where my coordinate system is going to be. Oftentimes in engineering, for some reason, right, we could pick downwards to be a positive X. Don't have to. I could put upwards to be my positive X. But a lot of times when you have things hanging and displacing in structural engineering, when we talk about deflections of beams, we have downward being positive because that's what gravity does. It always pulls things down. We just always talk about it as being positive deflections. But that's what we could do. I could rearrange this and do it with X being up. It's just some of my signs would change and I'd still get the right answer, okay? But I get to pick. So that's it. There's no other dimensions. There's that 0.3 meters, but that's kind of not part of our free body diagram. That's it. There's my free body diagram is done. I cannot stress enough how important free body diagrams are. It leads you to the right answer. All right, step two. Equations of motion. Is that what step 2 is? Write down equations of motion. Okay. EOMs. EOMs. Okay. My equations of motion, I only have one direction at this point, right? Because it's a 1D problem. There's no Y component. So my sum of the forces in the X direction is equal to MAX. Right? There's no vectors in this at this point because I'm only looking in the X direction, right? There's no multiple components. So that's it, okay? So then now what I do is I expand out what those forces are. I look to see, all right, what are my forces? And I just expand those things out. So what do I got? I got mg minus kx. Right? Those are my sums of my forces. I got mg in the positive x direction being down, and kx is going up, so it's a negative. You gotta be really careful of these things. You gotta be very meticulous as you go through. This is a very simple example, but if we go on, very meticulous on which direction these forces are acting, and then which signs we put on there on our diagram, or in our equations of motion. Right? And that's equal to max. mg minus kx is equal to max. At this point, what I'm after is acceleration as a function of x. I gotta get to velocities, right? So then I just, via algebra, solve for ax. Ax is equal to g minus k over m times x. Right? So there is my acceleration equation, right? Now, at this point, we're starting out what we have done in the class so far, right? In the class so far, you were given this, right? And in fact, there was a problem that we did with that spring. Remember, like I just mentioned before with the vibrations, we were given that equation, and it was almost identical. I mean, it was in this form, but this was 32.2 in that problem. If you look back in your notes, and that K over M was like a value that they gave us. Okay, so there we go. Okay, so now at this point, what kind of problem is this? Acceleration of function of position, right? This is acceleration of function of position, right? Because it's going to, how much the acceleration is depending on how much that spring is stretched out. And so that's what we do. So then the next step is kinematics, right? 3. Kinematics. Right? And this is going to be an accelerate. We noticed that acceleration function of position. And so what you do is you look back up in your notes and you see, how do I handle acceleration as a function of position? It involves using the chain rule. We'll go to this. AX is equal to dv dt. And we could slip in the chain rule, dv dx dt. Dx dt is just the velocity. Right? So this is equal to v dv dx. Right? Is a of x here? We have a value for that. That's just going to be g minus k over m times x dx is equal to v dv. So I just took this dx and I put it over on that side over there. Right? And I left the v dv part on the right-hand side. And then we integrate this. Okay. This is integration with respect to x, and we know that this thing's starting out at 0 deflection and it's going to 0.3. Right. The problem statement says, what's the velocity when it gets to 0.3? That's where I put that 0.3. I could just put in an x right here and leave that value out, and then I get x as a function, or velocity as a function of x, and then I can put in my x later, and then I can go from there, or I can put it in right now. Right? In this case, I can put it in right now. And this is going to be going from 0, it has 0 velocity, and it's going to VF. And that's what I'm after, is that VF. I'm after that VF. Okay? All right. I am 100% okay. Then all you would have to do at this point is you have to put in these numbers, right? So let's put in those numbers. Just kind of, I want to show you something about what I expect on the homework. So this is in meters. So this is 9.81. Integral from 0 to 0.3 of 9.81 minus my k is 1.8. My k is 80 over my mass, which is 1.8. dx is equal to v dv, going from 0 to vf. All right, so at this point right here, this is what I have to solve. I am 100% okay if you get to this point right here and you leave it in that form and then you give me the answer, right? Because if you use your calculator, yes.
Is there supposed to be an X?
Yeah, I wasn't done yet. Hey, it works every time. I wasn't done yet. I was missing that X. I was just going to say, what's wrong with this? Okay. Okay. So I'm 100% okay with you getting to this right here and then go like this. Answer, right? VF is equal to 1.37 meters per second. 100% okay, right? I know that, like, Anika she's been posting the solutions to the homeworks, by the way. I don't know if you've noticed that. After the homework's due, like the next week, she posts the solutions. She's worked out all these problems herself and a beautiful solution. She has good handwriting and everything. She gets to this point and she does all the math by hand, right? And that's fine. And if you want to do it that way, you could see the math. She's not jumping to the end with the calculator. For you guys, totally fine. jump to the end of that, right? Because I don't care if you remember and how to take the integral stuff. Let your calculator do that work for you, right? In fact, I highly encourage it because it literally it works better. You'll get the right answer, and you'll probably get the wrong answer if you try to do it by hand, okay? And then go from there. So totally fine. But I would get to the point like this where I actually have all the numbers. So let me see what it is that you put in there, right? Because I think that's important. Let me see what you actually put in. This is what you could actually put in to the calculator to make this thing work. So I want to see that, okay? Right? And then the last step was solve, but we kind of already did that. Yeah, one other comment here. Right, last step was solve. And that kind of was this right here, right? When we carried out that solution. It's kind of cool, right? That we just start out with this, right? We start out with just this right here, and we were able to solve for what the velocity was when it hit the ground, starting from scratch. They didn't tell it. We didn't cheat. We actually we derived the equations that we needed ourselves. The other thing I wanted to mention, she sent out a notice. A lot of you still aren't sticking to the homework requirements, like how to format it and stuff like that. So she set that out, and she said she's gonna start docking people if you don't do that. If anybody wants this, I have this. This is for GoodNotes. Anybody use GoodNotes? Yeah. If you want this engineering paper background, I have it. If you want it, maybe I'll just put it on. I'll put it on Canvas. I think same thing if you're using another like tablet. That's fine too. It's just a PDF, and then you just make it as a template. Just gonna start docking you for it. Okay. All right, let's do the next one. A little more complicated. Okay, so this is this little block right here, sitting on a ramp. Okay, block sitting on a ramp. It's got a string or cable of some sort coming down. There's a pulley right here in the middle, right? And you can imagine, and this is a frictionless surface right here. You could do it with friction, but in this case, it just makes it more complicated. We're going to do it without friction. It tells the slope of it. Right? If I pull down, you can imagine right here, if I pull down with a force P, and I pull hard enough, right, I can make this thing go up the ramp, right? And if I let go of it or I pull less, I can let it go down the ramp, okay? And so what this problem asks for is what P do I need in order to apply, what applied P do I need in order for this to accelerate up the ramp at 2 meters per second squared, and what P is required for it to go down at 2 meters per second squared, okay? And if it just tells you that if I didn't apply any P force, it would fall down faster than 2 meters per second squared, okay? Or it would be a faster acceleration. Right? And these ones, again, sometimes they look a little scary at first. I'm like, oh my God, what do I do? Just stick to the plan, right? Stick to the plan. We're gonna do a free body diagram, right? We're gonna do equations of motion. Step 1, free body diagram. Okay? And after we do that, we'll do equations of motion. Then we'll do kinematics as required, which is a little bit different form this time. Okay. All right, free body diagram. A lot more going on in this one. Isolate the object. Done. Okay. Just one point right there in the middle. Force is acting on. What do I got acting on this guy? Always a given. Gravity. Always a given. Somebody's got to yell that one out. Right. Its magnitude is going to be mass times gravity. Okay, what else? Force P, right? P's got a couple different locations, right? I'm pulling it right here, so obviously it's going to be there, right? But then also, it'll go this way too. Okay? Tension in that cable is going to be constant as it goes around that corner. Later on, when our pulley has mass to it, that's not the case. That isn't continuous P across, but when it's a frictionless pulley going around that corner, that's going to be the same P, right? That cable will be pulling both directions. What else? We got one more. Normal force. Ooh. Normal force acting like that. okay? So there's all my forces, right? And that's all my supports and forces acting on this object right now. But we're not done, right? We have to label, we have to come up with a coordinate system and label any dimensions and stuff, right? I hate doing this, I hate it, I hate doing it, but I'm gonna do it because it makes your life easier. I hate doing it because then later on, you guys are going to try to do this, and then you're going to do it in an inappropriate place, and then it's not going to work, and you're going to lose some things. But for this particular problem, it makes it a lot easier if we set up our coordinate system like that. We can do that, right? I think this might be the only time, I think this is true, the only time in this class where you have to do that, even in a homework problem. The homework is where I'm a little scared. In our example problems, I don't think we rotate our axes again. But it just makes our lives a lot easier if we do that. Because then it lines up with the P force and R. Could you do it if you didn't rotate your axes? Would it work? Yes. Right. But the reason it's a little bit easier here is because it's talking about its acceleration up and down in 2 meters per second. It makes it a lot easier if that 2 meters per second squared, right? It's either along the x this way or along the x that way. Otherwise, I would have to take that acceleration, and if I put my x and y like this, right, I would have to turn this acceleration. I'd have to look at its components in the x and y direction and break it in, which is fine. You could do that. It just adds a little bit more work if you do it that way. Okay, so just later on when we talk about objects rotating and being attached to strings and stuff like that, you don't want to rotate your axes because the accelerations it gets weird. We'll deal with that later. Okay, so then some other things another thing we have to do is label coordinates, right? So this is one thing, or we label the coordinates rather, the dimensions. So I need to label this, right? That is 20 degrees, right? 20 degrees, right? It's given over there on the right-hand side. So that angle right there is 20 degrees, right? We also want to do this. I'm gonna move these to this side. These guys are gonna have to, I'm gonna have to look at, in a few minutes when I sum my forces, I need these forces to line up with the x and the y direction, right? They're not now, they're off in some other direction. So I'm gonna break it into its components there. So it's going to have a little bit going this way and a little bit going this way. Right? And same thing with this one. It's going to have a little bit going this way and have a little bit going this way. Sometimes I like doing that. So when later on when I go to sum my forces, it's really obvious what they are. But this is kind of nice because now I can see, right? When I go to sum my forces in my y direction, I want this component, these components, right? Those are in the y direction. My sum in the x, there are these ones, right? It's kind of nice to be able to do that, okay? So then I should probably label some angle. Oh, same thing with no, that one lines up. Yep, so those are the only two. I got to label, this will be the 20 degrees here, and this will be the 20 degrees here. Right. You're going to have to do that quite a bit in this class to try to trace around what it is for your different angles and stuff, right? And you have to come up with a system for it, right? You gotta go, this one's 20, that one's not 20, so that one's 20. This is the not 20. You got a way of doing it, right? Everybody's got their own way. So come up with that, because we do this a lot in this class. Figure it out, right? I mean, you could do I think if you extend them out like this, right? Well, that's 20, that's 20, that one's not 20, and that one's not 20, and this one would be 20, and that would be 20, right? There's ways of getting around to it, right? I think that's it. I think if you think of that, if these things continuing through, remember that? I forget what those are called. What method that is, right? This. Yeah, this is 20, not 20, 20, which then across the other side would be 20, right? So there's ways to do there. Come up with your system that works for you. That's it, okay? Free body diagram done. Everything's labeled, all dimensions are labeled, we're all good to go now. So now we're ready. I cannot underemphasize how important this is. This is beautiful, it's laid out nice, I see all the components, it has all the dimensions labeled, so when I go to this next step, super easy, right? Next step is equations of motion. EOMs, okay? Right, we still haven't talked about how to go about solving this yet, right? And it's okay. You just start out doing these steps, and then eventually it'll come out to be like, oh shit, that's what I have to do to solve it. Okay, so stick with it. Right. So some of the forces in the x direction. And what we do is we just come up to our free body diagram and say what forces are acting in this x direction. Right. Well, I have a positive p right there. Right. I have a negative mg times sine of 20, and I got an mg sine of 20. You literally look to see what's acting in that. That's it, those three, right? And so then I write those three down in the x direction, right? So that'll be p, that's positive because it's acting in the positive x direction, minus mg sine of 20 minus p times sine of 20. Okay, that's it. That's the sum of my forces in that direction. Okay, and what's that equal to? MAX. Okay, and I come in and I do in the y direction. Sum of the forces in the y direction is equal to, so we come up here and say, what's acting in the y direction? Well, I got this normal force right here. I've got this component of mass times gravity, and I got this component of my p force. That's it. Those three forces. Right? No other forces acting on it. So then that's why I just write those down. I got p minus mg, cosine of 20. What's that? It should P be
Like for the y direction.
Yeah, that's I wasn't done yet. I wasn't done yet. Absolutely. PB. I was like, PBN? What the hell's that mean? Like some slang you got going on? Cosine 20. Thank you. That's very important. Minus P cosine 20 is equal to MAY. Thank you. That's actually very important because we wouldn't have been able to solve it otherwise. All right. So there's it. There it is. Right. My two equations of motion. And we look to see. It's kind of nice sometimes just to say what do we not know in here, right? Just to take a step back. Like I'm after P right here, right? I know my mg. I don't know P. Right. And then this AX right here. And what's AX gonna be? Huh? Up with this problem statement right here. Oh my God, what the? In this problem statement right here, right? It tells it we're trying to solve for this to be equal to something. So when we get down to the solving stuff, in one case I'm gonna set it equal to 2 meters per second. The other one I'll make it equal to what? Negative 2 meters per second, right? And so that'll give me these two different answers there, right? So just kind of show you what, like, this is it. This is what I'm going to need to solve it, just that direction, right? The y direction, right? Things that we don't know here, right? I don't know the normal force, right? I know the mg. I don't know the p, right? What about this ay? What's ay? Zero, right? It's not coming off of that. It's not coming off that ramp. Right. So just to show you, like, to solve this actual problem, all I need is this equation, right? I just need to solve this equation where that's equal to the mass times 2 or mass times negative 2. This direction, the y direction, I would need to use that if I was after the normal force, right? I could solve for what that p is, put it in down here, and I could solve for what the normal force would be, but I don't need it beyond that. And the problem statement doesn't ask me for the normal force, so I'm just gonna leave it out. If I had friction involved, right? If I had friction involved, there would be a friction component, right? There would be a friction that's resisting motion either that way or this way, depending on which direction it was going. And that would show up in my x equation, and that would be a function of my normal force. And my normal force, so it becomes a coupled equation, right? You'd have two equations and two unknowns that you'd have to solve simultaneously. We're gonna definitely run into those right now, but that's just to show you where we're headed, right? If it says, oh, do the same problem but with friction, this just adds a friction component, which is a function of the normal, so you need to solve both of these. You had a question in the back.
So did you just logically assume that AY is not a thing?
Yeah, just by if AY was a thing, right, is it would have to be accelerating up or down off that ramp, and it's not, right? It's stuck to it. It's just going to slide along it. Yep. That normal force is going to keep it from accelerating that direction. Yep. And otherwise, there's no other forces that would cause it to accelerate off that ramp. Yep. That's what I'm saying back to earlier when I chose to do it this way. It's really nice because I could say acceleration of the y is 0. If I had my x and y like this, only parts of it would be 0, right? Only the parts that were perpendicular to the ramp would be 0, and so you'd have to break that into its components. Okay? So now we're down to the kinematics. Right? There isn't much for the kinematics. We don't have to do any integration here. Right? The kinematics is just anything related to the geometry of motion and things that are given to us related to that geometry. And I would make the argument that the kinematics in this case is just that AX is equal to 2 meters per second squared or negative 2 meters per second squared and AY equal to 0. I would say that I would make an argument that that's our kinematics in this case. They just tell us what those things are. It's associated with that, okay? For solving. Okay, so we'll do it. You have to do this twice, right? One is going to be P minus mg sine 20 minus P sine 20 equal to mass times 2 and 2 P minus mg sine 20 minus P sine 20 equals mass times negative 2. Right? If you plug in all the known values, you solve for this P, you get P equal to 1.63 newtons. And then this would be going up, right? And then the other P to keep it from at 2 meters per second down would be P equal to 0.412 newtons down. Done. Okay. I do take a minute here. I didn't put in my numbers here. Wait, if you were to do your solution, right, I would want you to put in, like I said, put in the actual numbers of everything that you know mg, right? And mass, mg and mass. And so you would put those in, right? And then I'd want you to do that and then jump to this answer. So I know what you put in there. And that's for your own good, right? Because then I know what went wrong, and Nika knows what went wrong, especially on an exam. Was it just simply you put in the calculator wrong, you fat fingered it, or is it because you put in the wrong numbers, right? So I want you to get to the point where you do that, right? And we don't have to look in the y direction because I didn't need the normal force, right? If I wanted the normal force, then I'd have to look in the y direction. The other thing to be really careful of, I'm really super loose with this, and I warned you from the get-go, is units. Be very careful of your units, right? I just have done this long enough, and I find units so boring. But they are still very important, right? Everything goes in kilograms, everything goes in newtons, everything goes in meters. And if you do that, everything works out, and your units will come out in kilograms, newtons, or meters, right? If you get given something in kilonewtons, make sure you turn it to newtons when you go in, right? If they tell you, just be really careful when you go into there. English units, right? Everything goes in pounds and slugs. Fucking slugs, right? No? Nobody has any problems with slugs? I hate slugs, thank you. Right? Did you know there's one called a slinch? Yeah, when you divide gravity when you divide your pounds by gravity in inches per second squared, it's a slinch. Isn't that weird? So dumb. So dumb. We are so dumb. So dumb for using that system. A slinch. Just be very careful. Like I said, from the get-go, I'm so loose with it. I apologize. So you may go back and just verify the kilograms, newtons, right? Pounds, slugs, feet, pound, slugs, and feet, and then everything turns out all right. Okay, so now that was Cartesian coordinates, right? Let's talk about normal tangent coordinates because it works for this too, right? So normal tangent, right? If you recall, normal tangent is things moving along its path. You have two coordinates and they move along with the object. One's going to be tangent to the path, right? And the other one's going to be perpendicular to that. That's going to be their EN direction and their ET direction. In that direction, we define velocity as just being v in the ET direction or ds dt in the ET direction, right? Acceleration was this, AAT in the ET direction plus AN in the EN direction. AT is just the change in speed in the ET directions. That's the change in speed in the ET direction. And then in the AN direction, it's going to take one of these forms right here. Right? Usually it's going to be this guy right here, v squared over rho, or rho omega squared. Either one, depending if I know omega or if I know the velocity. Right? So that's just a little quick review of what the kinematics looked like. Okay? So for our equations of motion, right, all you really do, pretty quick little derivation, is I set this thing up and I sum my forces in the t direction, and that's equal to mass times acceleration in the t direction, or mass times v dot. Then I look in the n direction, right? And I sum my forces in the n direction. So you in your free body diagram, you clearly label where the n direction is and the t direction. And then I sum my forces in the n direction, or I sum my forces in the t direction. And then they're equal to the acceleration in those same directions, right? And so I'm going to set this up. In the n direction, it's going to be mass times an, which is either v squared over rho or mass times rho omega squared. Okay, that's it. We're done with the derivation in those directions. We got 8 minutes. We could do an example. Okay, let's do this. Right? I think the original Luke Duke is driving General Lee over the crest of a hill, as shown. You didn't grow up with Dukes of Hazzard. I did. Right? Maybe they did a reboot of it. Maybe you saw that as the thing. Anyways, over the crest of a hill is shown. The crest of the hill has a radius of 200 feet. So this is a 200-foot radius that is traveling around. Okay, the car weighs 3,500 pounds and is traveling at a constant speed, neglect friction, and it asks us to find the speed that the car can travel without leaving the surface. Or I like to think of it better is what's the minimum speed it has to go in order to jump. Okay, that's a cooler way to think of this problem because it's all about being cool. Okay. This is my version of driving of a car. I thought this was funny because we used to draw in high school. It's real, right? Or in high school. As a college professor, I still draw them like that. Look at mine over there. Not much better. Like I said, it's just an unfortunate part. Those of you that are gifted with being able to write well and draw well, it is a gift because us. Right? The rest of us, no matter how hard we try to be cleaner and neater, it gets worse, right? Like if I really focused, if I was like, I'm really going to try to draw a car, then it would turn out worse every time the more I concentrate. So thank your genes for being able to draw. I really wish I could. Okay, so here we go. What do? How do we find this thing? You don't panic, right? You stick to the plan. The plan is we draw a free body diagram, right? Every time. F, B, D. Every time, okay? And so we come in, isolate our object, that's the car, right? We're trying to figure out what's happening right up here where it's jumping, right? So we're gonna draw it at this state right here. And so what do we have acting on this car? Yeah, good. See, you guys are there. There's gravity, mg, and what else? Normal force, right? going to talk about that one in a few minutes here, but right now we draw it with the normal force that direction. Okay. How about the coordinates? Yeah. We're going to do normal tangent, but which way? Where are they pointed? Yep. So we got one this way, right? Tangent to the path. That's ET, right? And then I got one acted this way right here, and that'd be EN hat. Right? So part of these problems is figuring out where, right? This is a circle, right? Going around like that, right? It's going around, and so then ET, right? My ET is tangent to the path. So at this instant, ET is pointed that way, and EN is pointed back to the instantaneous center of curvature. So that's that. Pointed back down like that, right? And that's it. That's all I put in this. That's all I put in this free body diagram. I got mass times gravity up, normal up, ET's that way, EN's that way, okay? 2 is equations of motion. EOMs, right? And we don't have to transfer them into other coordinates or anything like that, or look at the different components because they line up. So you just come down and you just look in the different directions. So I look in the T direction. T direction first, right? Sum of the forces in the T direction are equal to MAT. Right? Then I look in the N direction. Right? In the N direction, it's going to be sum of the forces in the N direction is equal to MAN. Right? And so we expand these things out. What are the forces in the T direction? Right? Just look at our free body diagram. What forces are acting in the T direction? 0. Right? There's nothing acting in this direction, right? I just looked at my free body diagram and what's doing that? When would I have a force in that direction? Friction, yeah, if there was some friction going on, or if I was accelerating, right? If Bo was stepping on the gas and the thing was accelerating, right? If it was accelerating the direction, there would have to be a force acting in that direction, right? Which means there would be acceleration in that direction, right? So there would be an X component. Right now, at a constant speed, there is no forces in that direction, which means there's no accelerations in the direction. So this is all just equal to 0. Oops. Yeah, 0 is equal to 0, basically, is what that T direction. So there's nothing really happening over there. Both of those guys are 0. Okay, in the normal direction, though, there's more going on. I should also point out, we could do this, right? This acceleration in the N direction, that's going to be equal to mass times velocity squared over rho. Right? That's where you slip in that AN component, right? And again, I could choose, if you can go back up here, I could choose which one I wanted to use. I could use the V squared over rho or the rho omega squared. But I'm trying to figure out the velocity that it needs to get to when it goes around. So I'm solving stuff in terms of velocities. And so down here, right, I'll just set that equal to mv squared over rho, right? And so let's expand this thing out. I have mg acting in the positive En direction. Right? I come back up here and I say, well, what's acting on this? Well, I got mg acting this way and normal force acting that way, right? So it's mg minus n minus the normal force is equal to mv squared over rho. Okay, we're almost there. The one thing we have to talk about, we have a problem here at this point. Mg, I know what that is. Normal force, I don't know what that is. Velocity, I don't know what that is, right? So I got 2 unknowns and I got 1 equation, right? So I have to make some assumption right here. And the assumption I'm going to make is what this normal force is. What's that normal force going to be? 0. It's going to be 0, right? It's going to be 0. When it's jumping, that's the bifurcation point, right? Would be the difference in when it's equal to 0, it means it's just going to start lifting off because we're trying to find the minimum speed required so it lifts off. And so in that case, that normal force will be equal to 0, right? Right at that point. Can that normal force be acting down and end up being a negative value? Yes, right? If it was like a roller coaster or something like that. But if the thing's jumping in the air, that normal force is right at the point where it leaves the surface. If I go slower than this, there'll be a normal force. If I go faster than it, it will not be a normal force, right? And so we find that point, right, where this thing's equal to 0. So we set the normal force equal to 0, right? That's where it jumps, right? So you plug in your values. Oh yeah, actually your masses cancel out here too, right? The mass is on both sides, so it is not dependent on the mass of the vehicle. So this will be 32.2 is equal to v squared over 200. Right? Plug that sucker in your calculator, and you get v is equal to 80.2 feet per second. Is that minimum speed? That's our answer, right? You put that in miles per hour. That's what we usually think. That is 54.7 mph. So if they travel at 54.7 miles per hour, they will just stay right on that curve and keep going around that corner. They'll have enough acceleration down to make that happen. That acceleration down towards the center is caused by that mass times gravity term. That's causing us to accelerate down towards the middle. If you go faster than that, that mass times gravity won't be enough to accelerate you back towards the middle, and you'll take off, right? And you'll jump. Cool. Okay. Next one we'll do is this. This is the fun one. Right? These people jump off of a bridge and they're attached to a cable, and what kind of force do they have there? Okay, break. Is everything gonna be okay? The answer